All right, so you have 15 players. And let's talk about both parts while we're here. Part A, you're trying to fill 5 positions. So you can break this into a set of tasks. So what are your 5 tasks to make a basketball team of 5 people, right? Pick the first person, pick the second person, pick the third, and so on. So T1 is picking the first person. You got 15 ways to do that. To pick the second person, you've got 14, and then 13, and 12, and 11. So it's just the product of those numbers is your answer for the first part. For the second part, the center must be one of 2 people. Okay, so the center is one of the positions on a basketball team. So the center must be one of 2 people. So let's pick the center first. So task 1 is picking which player is going to be the center, right? And how many ways can you accomplish that task? It's 2, right? All right, and then you have to pick the remaining 4 positions, and there's no restrictions on that, except the person that you picked for center can't be another position as well. So how many people do you have that you can choose for T2? Right, so you've got 14 and 13 and 12 and 11. So it's just the product of those. And most of these problems are like this. It's going to end up just being a product of, right, usually a sequence of numbers. So other questions? So we worked all kinds of versions of the product rule yesterday, right, which is like picking people on a basketball team. So a task that you're trying to accomplish through a succession of subtasks. So do task 1 and then task 2 and then task 3. You can multiply the number of ways to do each task to find the number of ways to do your original task. So the sum rule is a little different. So if a task T can be accomplished by either T1 or T2. In other words, we can split it into doing either this subtask T1 or this subtask T2, but you don't have to do both, right? Either one will complete the task, and if there's n1 ways to do T1 and there's n2 ways to do T2, then T can be done n1 plus n2 ways. Bless you. Okay, so examples. Order a soup or a salad. So you go to a restaurant and as an appetizer they will bring you either a soup or a salad. And let's say that there are 3 soups and there are 5 salads. So your task is to order an appetizer. It's not really an appetizer. And you can do this as either T1, order a soup, or T2, order a salad. There's 3 ways to order a soup. There's 5 ways to order a salad. The total number of ways that you can order one of these is 8. Right, it's just the sum. And this should make some kind of sense, right? You're allowed to do either this or this. If you do this, you've got 3 options. If you do this, you've got 5 options. So in total, you've got 8 options. That's all there is to the sum rule. Right, you need to send a student or a teacher to a meeting. You've got 100 students, you've got 25 teachers. How many ways can you choose someone to go to the meeting? Right, you can either choose a teacher, there's 25 ways to do that, or you can choose a student, there's 100 ways to do that. So your task of choosing someone to go to the meeting, there's 125 ways. It's just the sum. And so sometimes we find combinations of these rules. For example, a variable name. So you got a programming language, and your definition of a variable is a 1 to 2 character symbol. Must start with a letter, which is A through Z. Second character is a letter or a digit. So your task T is create a variable name. Right, our question here is how many variables are possible? How many different variable names are there? So we're answering this question by saying, well, here's our task. Our task is to create a variable, and we simply want to know how many ways can we accomplish that task. That will tell us how many different variables there are. So how many ways can we accomplish this task? Well, we can split this into 2 subtasks. T1 is create a 1 character variable. Or T2, we might create a 2 character variable. Because we're told a variable is either 1 or 2 characters. So the number of ways we can accomplish this task is going to be the sum of how many 1 character variables we can create and how many 2 variable characters we can create. Well, let's look at T1. How many 1 character variables can we come up with? 26, right? It's got to be something that starts with a letter. So that's just 26 possibilities. But for T2, we're trying to create a 2 character variable. And that itself we can break into a succession of tasks. So we could take T21 is pick first character, and T22 is pick the second character. So how many ways can we pick the first character? Well, again, that's 26. But how many ways can we pick the second character of a 2 character variable? 36, right? Because we can pick a letter or a digit. And so the number of ways we can complete task 2 is the product rule, 26 times 36. So the total number of ways that we can accomplish task T is 26 plus 26 times 36. So it's a combination of sum and product, that's all. All right, good on sum rule. All right, so let's talk about subtraction. So the idea of the subtraction rule is this thing that we observed a while ago. If A1 and A2 are finite sets, the number of elements in their union is no bigger than the number of elements in A1 plus the number of elements in A2. But in a lot of cases, this is going to be bigger than this. Because if there's overlaps, things that are in both A1 and A2 will get counted twice over here. Whereas when we take the union, we only count it once because we don't have duplicates in our set. So we have to actually subtract the number of things that A1 and A2 have in common. So we have this rule for the number of elements in a union. It's the sum of the elements in each set minus the number of things that overlap. And this we can use as something called the principle of inclusion exclusion. So let's see an example of this. So how many 8-bit strings start with 1 or end with 2 zeros? So an 8-bit string, 8 ones and zeros. Some of these strings may start with a 1 in the most significant bit. Some of them may end with a 0, 0 in the 2 least significant bits. We want to know how many strings fall into that category. How many 8-bit strings start with a 1 or end with a 0, 0? And we can use this principle of inclusion exclusion and do this pretty painlessly. So let A1 equal the set of all 8-bit strings that start with a 1. And let A2 be the set of 8-bit strings that end with a 0, 0. And so this question is really asking what's the number of elements in the union of these two sets. And we're told that that's the number of strings that start with a 1 plus the number of strings that end with a 0, 0. But we have to subtract the number of strings that are in the overlap. Otherwise, they would get counted twice. Okay, how many 8-bit strings start with a 1? So these are strings that look like this. So how many ways can we fill in 7 blanks with 1s or 0s? Okay, every bit can be a 1 or a 0. So if we broke this into subtasks, right, there's 2 ways to fill this bit in, 2 ways to fill this, and those as well. And so there's a total of 2 to the 7th ways to fill in those 7 spots. And as computer scientists, we also know that the number of 7-bit numbers is 2 to the 7th. Right? The number of 4-bit numbers is 2 to the 4th. The number of n-bit numbers is 2 to the nth. Agreed? So that's the product rule sneaking in there, but it's also the way things are. Okay, A2 is a set of 8-bit strings that end with a 0, 0. These are strings that look like this. So how many such strings are possible? 2 to the 6th, good. Because we got 6 blanks to fill in. There's 2 to the 6th ways to do that, so there's 64. All right, what about the overlap? So if something is in A1 and also in A2, it means it begins with a 1 and it ends with 2 zeros. So we have 5 blanks to fill in, and there's 2 to the 5th ways to do that. So the total number of things in the union, bless you, is 128 plus 64 minus 32, which is 160. So that's the subtraction rule. And we can use this for all kinds of situations. So let's see. So 25 students in CSE 215, 45 students in CSE 222. So how many computer science students are there in the program right now at Clark? Well, it's not just 45 plus 25, right? Because most of the people who are taking 215 are also taking 222. So we need to know what the overlap is. So let's say 20 students in both CSE 215 and CSE 222. So now we have enough information to know how many students are in the CS program this quarter at Clark, assuming they're all taking 215 or 222. So we've got 25 plus 45 is 70 students, but 20 students are actually taking both, right? So 25 plus 45 minus 20 means we got 50 students. Right, so the steps I skipped here are these ones that we used over here. So A1 could be the set of students in 215, A2 could be the set of students in 222, and the number of students that are taking either of those is 25 plus 45 minus the number that are overlapped. So 50 students taking 215 or 222 or both. So there's a homework question that plays with that also. All right, so this brings us to the Pigeonhole Principle. Has a nice cadence to it, yes it does. So what's a pigeonhole, right? You have a box on its side and it's got dividers in it. And there's all these little squares now and pigeons can hang out in there and do their thing. And when people used pigeons to deliver messages or whatever, right, they would train them, and after they were done making their delivery, they'd come back and they'd go into their particular hole in this little area. So here's the basic idea of the pigeonhole principle. If you have 30 pigeonholes, you can have at most 30 pigeons occupying those pigeonholes, assuming you're not allowed to double up. If you have 30 holes and 31 pigeons, and they're all going to go into a hole, there's going to be at least one hole that has 2 pigeons in it. Okay, if you have 30 seats and you have 31 students, at least 2 students are going to have to share a seat. Okay, that's the whole principle that we're working with here. And it's pretty intuitive, right? Now, it could be that you have 30 seats and you have 31 students, and all 31 students are in one seat. That's possible, right? Or it could be that they're all spread out in different seats. The only thing this principle is saying is that there is at least one seat that has 2 students in it. It could be a seat that has 3 students in it. That's fine. But it's not possible to have only 1 student per seat if you only have 30 seats and you got 31 students. Okay, that's the intuitive idea. So here we can ruin it with some math. If k is a positive integer, and k plus 1 objects are placed into k boxes, then at least one box will contain more than one object. So k boxes, k plus 1 objects, and you're putting objects into boxes, there's at least one box that has more than one object in it. Okay, for example, 27 people. So given 27 people, at least 2 have the same first initial. How do we get that from the pigeonhole principle? Well, imagine 26 boxes. We'll label them A, B, C, D, X, Y, Z. And each person will be assigned to a box based on what their first initial is. We have 27 people, we have 26 boxes. There's going to be at least one box with 2 people assigned to it. And if 2 people are assigned to the same box, they must have the same first initial, because that's how we assign a box. So from the pigeonhole principle, we get the truth of this immediately. Bless you. So given 8 people, at least 2 were born on the same day of the week. So how do we apply the pigeonhole principle to that statement to see that it's true? There's 7 days in a week. Okay, we haven't mentioned boxes yet, though. Or pigeonholes.
Monday through Sunday.
Okay, so 7 boxes, each with a day of the week on it.
then they'll be in each of the boxes, and then you have an eighth person that has to have one of the 7 days of the week.
Okay. You're working a little too hard. Let the pigeonhole principle do the heavy lifting, right? I think what you're describing is simply putting each person in a box based on the day of the week they were born, right? So 7 people, each was born on a day of the week, put them in the box corresponding to the day of the week they were born, right? If you have 8 people, you're trying to put 8 people into 7 boxes. Pigeonhole principle says at least one box has 2 people in it. And since you put people in a box based on the day of the week they were born, that means at least 2 people were born on the same day of the week. And so there's the proof of it, right? Intuitively, it makes sense. And so when we try to use this, sometimes we skip over the pigeonhole principle and we start talking about the intuition. Well, each person could at best, have a separate day of the week, but then when you get to the 8th person, there's no extra day left for them, right? But that's what the pigeonhole principle does for us. And it saves us from having to justify this, right? So think about these problems in terms of boxes and putting things into boxes. Make sense? So we have a quiz worth 10 points max. And we have 12 students. At least 2 students got the same grade. So how can we use the pigeonhole principle to show that?
Do we have to say there are at least 11 students? Because, I mean, the way you wrote the pigeonhole principle, it says +1.
Mm-hmm.
But, I mean, that can be extrapolated to the
It could be anything bigger than or equal to k plus 1.
You have to say 12 is greater than 11?
Actually, so how many, what are our boxes going to be here?
Yeah, the grades.
Okay, so we have boxes based on the grade. How many boxes do we have?
Oh, yeah, I guess because zeros are grades.
Yes, we've got 11 boxes. Yeah, so only integer grades. That needs to be in here too. So put each student in a box based on their grade. We have 11 boxes, we have 12 students. There's at least one box with at least 2 students in it, which means those students got the same grade. And yeah, we can make this at least k plus 1 objects, right? Because if we have k plus 10 objects, right, we can just put the first k plus 1 objects into our k boxes and apply our principle at that point. And certainly adding more things to the boxes isn't going to take anything out.
So would it work if instead of using integer grades, you just said there was 101 students, and you could have 0 to 100%?
Yeah. Unless you can have fractions of a percent, which I do occasionally. All right, making sense? So are these fairly straightforward seeming? Right, just putting things into boxes and running out of space. So let's try one that's really not very obvious. So prove that any positive integer has a multiple consisting of only zeros and ones. Didn't see this one coming, did you? Any positive integer has some multiple of it consisting of only zeros and ones. So does this work? Well, 1 multiplied by 1, right, is an integer consisting of just ones and zeros, so that's easy. 2 times 5 is 10, so that works. What about 3? Yeah, so 3 goes into 1, 1, 1, however many times that is. 37 is 1, 1, 1. 4 times 25, 5 times 2, about 6. There's something. 7 should do something, but it starts to get a little hard to sort of figure out what these things might be once we get past the first few cases. But nonetheless, we can prove this. This is true.
Reading this first, it seems like a mathematical induction problem. Thinking about it, how would you go plus 1?
I've never tried to do this with induction. There may be a way. But we can do this pretty easily with the pigeonhole principle, which to me is really startling. We have to throw in some number theory.
You could say like there are less numbers, something like there are less numbers that have zeros and ones than all possible integers, something like that.
That's true, although they're both cardinality aleph naught, I think.
Yeah, that would be.
But up to a point, there's certainly less of these than there are those. So let's see how we can throw the pigeonhole principle at this. So proof. So consider the following numbers modulo n. So let me call our positive integer n. So we're going to consider the following numbers modulo n. 1, 11, 111, 1,111, 11,111, and so on. Just all the numbers that you can write consisting of just a string of ones. And I want to consider n plus 1 of these. So if our number is 7, I'm going to look at 8 numbers. 1, 2 ones, 3 ones, 4 ones, all the way up to and including 8 ones. Well, remember, when we work modulo n, every number is congruent to something between 0 and n minus 1. Okay, so make n boxes. And we're going to label them 0, 1, 2, up through n minus 1. Place each of these into a box based on its congruence modulo n. So take each of those numbers, put it into one of our n boxes. Well, we have n plus 1 numbers, and we're placing them into n boxes. What does the pigeonhole principle tell us? At least 2 of these share the same box. So at least 2 of these are congruent modulo n. Therefore, their difference is a multiple of n. And if we take these two numbers and we subtract the smaller one from the larger one, what do we get? We get a bunch of 1s followed by a bunch of 0s. And that is a multiple of n. And that's your result. So should we try this? Let's see if it really works. So let's take the number 7. I'm going to cheat and use a calculator. So this is congruent to 6. This is congruent to 5. Is it 2? Are you ahead of me? Cool. So we could have stopped right there. This one's going to be 1, 4, 5, 6, 7. Let's go one more. All right. So we've got 8 numbers. We found 8 congruences between 0 and 6, right? 7 possible boxes, 8 things going into them. At least 2 of these must be the same. Well, in fact, the 4 and the 4 are the same. And in fact, the 1 and the 1 are also the same. So we could have done this any number of ways. We could have done this minus that, or we could have done this minus that. Oh. All right, so we have 8 numbers, each congruent to something between 0 and 6. So 7 possible congruences. So we've got to have duplicates in here, such as the 1 and the 1. So this is, right, 1, 1, 1, 1, 1, 1, 0 should be congruent to 0 mod 7. And this 8th one minus the 2nd one, that should also be congruent to 0 mod 7. Right, so that's a multiple of 7. And so is that. And in this case, when we were computing this, we actually came across a pattern of all 1s that was a multiple of 7, so we could have stopped there. But the principle is general, right? Given a number n, write out n plus 1 of these, find their congruence modulo n. 2 of them will be the same. Subtract the smaller from the larger, you'll get something with just 1s and 0s, and it's a multiple of n. So that's a kind of unexpected application of the pigeonhole principle. All right, so let's look at the generalized version of this. So given n objects and k boxes, at least one box has what we call ceiling of n over k objects. So ceiling is the smallest integer bigger than or equal to x. We talked about this briefly a while ago. So ceiling of 2 is 2 Ceiling of 2.1 is 3. All right, because 3 is the smallest integer, bigger than or equal to 2.1. Ceiling of 2.999 is still 3. Ceiling of 3 is 3. Ceiling of 3 point just a little bit more takes you up to 4. So if you have n objects in k boxes, at least one box has whatever the ceiling of n over k is. So if n is k plus 1 over k is something slightly bigger than 1, right? So the ceiling of that's going to be 2. So this is just the particular pigeonhole principle we started with. K plus 1 objects, k boxes, at least one box has 2 objects. But for example, if you have 52 cards, and they come in 4 different suits, so clubs, diamonds, hearts, spades, 13 of each. How many cards do you need to pick to guarantee at least 3 of the same suit? So you got 52 cards, there's 4 suits, and you want to pick cards until you've got 3 cards that are the same suit. How many cards do you need to pick to guarantee that you can do this, right? Certainly if you pick all 52, you're guaranteed, but what's the smallest number that you can pick to be guaranteed that you've got at least 3 of the same suit? So make 4 boxes labeled with the different suits of the cards. Take each card, put it into a box based on whether it's clubs, diamonds, hearts, or spades. And now this question is asking, how many cards do you have to put into your boxes to guarantee that at least one box has 3 objects in it? So we're saying find n such that ceiling of n over 4 is equal to 3. Right, because if you have n objects going into 4 boxes, this is how many objects have to appear in at least one box. So find an n so that when you divide by 4, your ceiling is at least 3. Well, if n equals 12, 12 divided by 4 is 3, right? So that will certainly work. But there's smaller numbers too. If n is 8, n over 4 is 2, ceiling is equal to 2. But if n is anything bigger than 8, for example, if n equals 9, this will be the ceiling of 2.25, which is 3. So if you pick 9 cards, you're guaranteed to have at least one suit that appears 3 times. Yeah?
Generalized principle. Why isn't it at least one box has at least n over k objects?
Actually, one box has, yeah, at least. Thank you. Right, because they could all go into one box. Right, so this makes sense, right? If you're picking 9 cards, you could pick a club, diamond, heart, spade, club, diamond, heart, spade. You've got 2 of each suit. You pick the 9th card, it's going to be a club, diamond, heart, or spade, and whichever one it is, now you've got 3 of that suit. Right, that's the intuitive way of looking at this, but this is a formalized way to do this. All right, so we'll look at another example of this tomorrow, and then we will move on to permutations and combinations. And that will take us to the binomial theorem, and that will conclude this chapter.